Okay, we stopped here last week. Okay, so far, what we are talking about in class is kind of white box attack. What does it mean? It means that we have to calculate the gradient. We need to calculate the gradient when doing FGSM. When calculating the gradient, we need to know the parameters of the model. After knowing the parameters of the model, we can calculate the gradient and add the noise to the image. This kind of attack, which the parameters of the model are known, is called white box attack. In Chinese, sometimes we call it Bai Shang Gongji. The Bai Shang is an animation. This is Bai Shang, but it is not very important. It's not important, don't care about me. You might think that, because we needs to know the parameters of the network to apply this attack. This attack is not that threatful. The reason is that for general online service, of course, what you attack is others' model, which is a general online service. The parameters of the model are unknown for you, so attacking an online service may not be easy. In fact, if we want to prevent our model from being attacked by others, we just don't put our own model on the internet and open for everyone. Maybe our model will be safe if we do that. But is it really true? Attacks without knowing the model parameters are called black box attack. Is a black box attack possible? Black box attack is possible. How to do a black box attack? Until now, when we are attacking, we need to calculate the gradient. The parameters of the model are needed when we calculate the gradient. So how does the black box attack work? Black box attack is done like this. In our homework, which the TA just announced, we perform black box attack. Suppose there is a model on the internet. You can't get this model. You don't know what its parameters are. This is actually the model on Judge Boy. You don't know which model is used by TA. You don't know what its parameters are. Then what should we do? Assuming that you know which kind of training data is used to train this network. Then you can train a proxy network. In the other words, you train a network and use this network to imitate the network which we want to attack. If the network we want to attack and our proxy network are trained with the same training data, maybe they will be similar in a certain degree. If the proxy network and the network we want to attack are similar in a certain degree, then we only need to attack the proxy network. Maybe use this attacked image as input and pass it through the network with unknown parameters. The attack will still succeed. This is actually what we do in our homework. So in the homework, you will use a trained image recognition model from somewhere. This is your proxy network. On your own machine, you attack your own network on Colab. Send it to Judge Boy and check whether this attack succeeds. Someone might ask that, what can I do if I don't have any training data? I don't even know the model I want to attack is trained on what kind of training data? In the homework, we know it is Sci-FAR 10. The model we want to attack is trained on Sci-FAR 10, so you can just use one model that is trained on Sci-FAR 10. You may be able to attack successfully. But what if we don't have any training data? This is not completely unsolvable. How to solve it? Assuming that this is the image recognition model you want to attack, you could just pass a bunch of pictures through it and see what it will output. Even if the online service doesn't tell you the parameters of the network, you can always input some images and see what it outputs. And using the paired data of input and output to train a model, you may be able to train a similar model and attack it as a proxy network. Is this kind of black box attack easy to achieve? It's quite easy to achieve. You will find that in your homework. The black box attack is actually very easy to succeed. This is the result in the previous paper. There are 5 different networks, which are ResNet 152, ResNet 101, ResNet 50, VGG 16 and GoogleNet. There are 5 networks in total. Okay, this column represents the networks to be attacked. There are 5 networks to be attacked in total. Then this row represents 5 proxy networks. On the diagonal, it represents that the proxy network and the network to be attacked are exactly the same. So, this situation is not a black box attack. The values on the diagonal are white box attacks. If you take ResNet 152 as a proxy network, it attacks the same network. That is easy to succeed. The number here is the accuracy. The accuracy of the attacked model. So, the value is the lower the better. Lower accuracy means your attack is more successful. You are on the attacking side now. You are not responsible for training the model. You are the attacker. The lower accuracy means your attack is more successful. You find the values on the diagonal, which are white box attacks. The success rate of this attack is 100%. That is, the accuracy of the model is 0%. Your attack will always succeed. But what if it's outside the diagonal? Which is for the black box attack. For example, you use ResNet 101 as a proxy network. To attack ResNet 152, the accuracy is 19%. Or, you use ResNet 152 as a proxy network. To attack ResNet 50, the accuracy you get is 18%. The values outside the diagonal are for the black box attacks. You will find that the accuracies of the black box attacks are higher than that of white box attacks. But in fact, these accuracies are also very low. Their accuracies are less than 50%. That is, black box attacks also have a certain possibility of success. But in fact, the black box attack is easier to succeed in non-targeted attacks. It is hard to succeed in targeted attacks. Assuming that you use a proxy network, and you want to turn a dog into a rabbit. If you input attacked image to the model you want to attack, you can make it misrecognized. You might let the machine recognize anything rather than a dog. But it's harder to specify it to become a rabbit. So, during the black box attack, the targeted attack is more difficult to succeed, while the non-targeted attack is still very easy to succeed. What to do if you want to increase the success rate of black box attacks? The TA also talked about a tip to pass the strong baseline. Ensemble's network. What about this ensemble network? The column of this table represents the network to be attacked. What does each row mean? You will find the name of each model and put a minus sign. What does it mean? That means we now put these 5 models together, but remove ResNet 152. We are looking for an attacking image that can attack all models except for ResNet 152. Let's assume that we don't have ResNet 152 on hand. But we have ResNet 101, ResNet 50, VGG16, and GoogleNet. Find an image that attacks successfully for these 4 networks, and see what happens on ResNet 152. In this picture, the below table is different from the above table. For the below table, off-diagonal places are for white box attacks. Did you find that the model accuracies in off-diagonal become 0%? As I just said, white box attacks are very easy to succeed. The values on the diagonal are for black box attacks. So this means that we want to attack ResNet 152. But we don't use ResNet 152. This is to attack ResNet 101. But not use ResNet 101. We use the other 4 networks. The values on the diagonal are for the black box attacks. You can find that when you do ensemble. That is, when you use multiple networks at the same time. You can find an attack image that successfully fools multiple known networks, and also fools a black box network that you don't know the parameters. It is very easy to succeed. You see the accuracies on the diagonal. Most of them are less than 10%. Okay, this is a black box attack. You will find out this attack is very easy to succeed. Why? Why even in the scenario of black box attacks? Your attack image for network A can be successful on network B? In fact, this is still an unsolved mystery. There is still a lot of space for research. The following is a conclusion that many people believe. There is an experiment here that looks like this. The origin of this graph represents a picture of a clownfish. This one is Nemo. It's a clownfish called Nemo. The place of Nemo in this picture is here. What is the horizontal and the vertical axis? They are moving this picture in 2 different directions. A picture is a very high-dimensional vector. Move this high-dimensional vector in different direction. The horizontal axis is moving in a certain direction. The vertical axis is moving in another direction. What about the horizontal axis and the vertical axis here? What direction do they represent? The horizontal axis here is on the VGG16. Whose direction can attack successfully? The vertical axis is a random direction. You will realize that although this horizontal axis allows VGG16 to attack successfully on other networks such as ResNet 50, ResNet 101, ResNet 152 and GoogleNet above, it looks like this. Later on, I realized that they have great similarities. The dark blue area between them is quite similar. What is this dark blue area? It is the range of pictures that will be recognized as clownfish. In other words, if you take a picture of this clownfish and add noise to it, and then you take this high-dimensional vector to move in this direction in a high-dimensional space, basically, network will still feel that it's a picture of a clownfish. For every network, as long as it moves in this direction, which is a random direction, it basically will be considered as clownfish. But if it moves in the direction that can successfully attack VGG16, basically, other networks seem to have quite high possibility to be attacked successfully. You realize, in the category of clownfish, the direction of the successful attack is very narrow. As long as you take this high-dimensional vector, which represents this picture, to move a bit, it will fall out of the area where it is recognized as a clownfish. It will fall out of the area where it is recognized as a clownfish, and it will be recognized as other categories. For every network, it seems that this attack direction could give quite similar impact on different networks. So, there is more than one paper which is believing for attacking in like this. You can know from the title of this article. It says that adversarial example are not bugs. They are features. So, a group of people is advocating that the reason of the success of attack is from your data, but not from the model. The results of training from different models look pretty similar. And the situation that the attack will succeed is not only for deep learning, but also for linear network and SVM. So, maybe, the main reason why the attack could succeed so easily may not come from the model, and it may come from the data. Why does machine misclassify one object as another object by these small noises? Because the features in the data may be just like this. With limited data, this is the conclusion that the machine could learn. So, maybe, the reason why adversarial attack could succeed is owing to the problem of the data. When we have enough data, maybe, there is a chance to avoid adversarial attack. But, this is just one of all opinions. Not everyone agrees with it. Just a certain group of people agree with this point of view. Maybe, a few years later, when you come to take the same course again, I may give you a different conclusion. Here, I'm just telling you that there is a group of people who believe that data is the flaw that makes the attack successful. Okay. For the signal to perform attack, we hope it as small as possible. How small can it be? In the literature, someone successfully made the 1-pixel attack. The so-called 1-pixel attack means that you can only modify 1 pixel in the picture. For example, in this picture, they modified a pixel. The changes in pixel are framed. They frame it, and frame it. They hope it, through changing a pixel in the picture, to make it misclassified by the image recognition system. But, actually, if you see from this picture, where this is the black part, representing the correct result of this image recognition before attack, and the blue part, representing the result of this image recognition after attack, you will realize that 1-pixel attack still has some limitations. Its attack is not really successful. Why? For example, this is a teapot. It is a teapot. We do 1-pixel attack in this place. The color of a certain pixel has been changed. The machine recognizes teapot as joystick. What is joystick? The joystick is a controller to play TV or computer game. Then, you will realize that this mistake is actually quite reasonable, and not as ridiculous as what we mentioned at the beginning. Like a cat to a starfish and a cat to a keyboard. It is quite reasonable of this mistake. So, it feels like this attack is not very powerful. This is about 1-pixel attack. In fact, there is an even much crazy attack method called universal adversarial attack. What does Universal's attack mean? So far, every picture is customized. You have 200. There are 200 pictures in the assignment. 200 pictures. You will find different attack signals individually. Then someone asked, is it possible to use a signal to successfully attack all the pictures? Because you say, each picture must have a different signal. If you want to hack a certain surveillance system today, that you want to make the identification of a surveillance system wrong, then you may need to really hack into that surveillance system. Every time receiving a different image, you have to customize and find an attack signal. Then the amount of calculation may be very large. If universal attack succeeds, actually you just need to stick this signal to the lens of this camera. Then if this attacked signal is very strong, just add this attacked signal. No matter what kind of image, it can be attacked successfully. You just need to put this signal directly on the camera. Stick to the camera. Then this camera is directly broken. No matter what it sees, it will recognize erroneously. Is it possible for universal attack to succeed? You can take a look at this paper. Universal attack is possible to succeed. In this paper they found a noise. They found an attack signal. This attack signal, added to so many different pictures, can make the image recognition system recognize erroneously. So far, the examples we give are all images. Someone might think that only the images have the problem of being attacked, and other type of data would be less likely to have this kind of problem. Not really. Other types of data have similar problems. Take voice as an example. Everyone knows that people do defect now. Someone will use speech synthesis or use voice conversion technology to simulate the voice of some people and to achieve the effect of fraud. In order to detect this defect condition, there is another ongoing series of studies about detecting synthesized sound. Today, although the speech synthesis system can often synthesize a fake voice, but for these fake voices, there is still a very high possibility that can be detected by a machine. These synthesized signals still has a fixed pattern. Compared with real sound signals, there is still a certain degree of difference that human can't distinguish, but the machine can catch. But the systems that can detect synthesized audio, which can detect a sound signal, is synthetic or not, would be easily attacked. The following is a real example. Let's play a synthesized voice. This is a synthesized voice. Anyone can distinguish this as a synthesized voice. This voice is deliberately synthesized with flaw. If today's speech synthesis system can synthesize sound, that people can't tell whether it's synthesized or not. The previous one is obviously bad. So you use this to detect whether it is from a speech synthesis system. It can tell you correctly that this sound signal is obviously synthesized. Okay, but if we were to add a little bit of noise in the sound signal, it sounds like this. You might ask, where is the difference between this new sound with noise and the original one? The human ears can't tell the difference between them at all. The noise is very, very small. No one can tell the difference between these two audio signals. And after adding this small noise to this sound signal, it doesn't sound better. But the same system that detects synthesized voice would feel that the sound is real, instead of synthesized. Okay, what I just gave is an example of voice. Will the text be attacked too? Text will also be attacked. In the homework, one of the tasks is to do question answering. Let machine read an article. Ask machine a question, and see if it can give you the right answer. Then there was a paper found out that, after adding why how because to kill American people, at the end of all articles, no matter what question you ask it later, its answer is to kill American people. So you can do adversarial attack on the text, and directly let this QA system always answer to kill American people. So no matter what kind of modality it is likely to be successfully attacked. Okay, so far, our attacks all happen in a virtual world. All happen in the digital world. After you load an image into the computer, you add the noise. And is it possible for the attack to happen in the real world? Is it possible to happen in a three-dimensional world? For example, there are many face recognition systems. If you are going to launch an attack in the digital world, then you have to hack into the face recognition system. When someone requests for this service, add noise to the face image. By doing so, you can fool the face recognition system. Is it possible to use this attack? Or add this noise to the three-dimensional world? Is it possible to add it to the three-dimensional world? Is it possible that someone puts a specific makeup on the face and fool the face recognition system? This is possible. It's more difficult to put on makeup. You know that if you sweat on makeup, you may lose your makeup. So makeup may not be a particularly good method. Someone discovered that it is possible to make magical glasses. After wearing the magic glasses, you can fool the face recognition system. The glasses don't look anything special. It is colorful and looks very trendy. When the man on the left wears these glasses, the facial recognition system will think he is the celebrity on the right. I don't know who is this celebrity. It doesn't matter. I'm not too familiar with the three-dimensional world. I don't know who she is. If you read this paper carefully, you will find that they have considered a lot of problems in the physical world. First, in the physical world, we can look at something from multiple angles. In the past, some people thought that adversarial attack might not be that dangerous. Why? For one piece of the image, you need to add a certain noise to make this image misclassified. But in the real world, you can look at the same object from multiple angles. Maybe the noise can fool the system at some angles, but there is no way to fool the image recognition system at all angles. But this paper has considered this point of view. It is not from a certain angle that he is recognized as the celebrity on the right. Looking at this person with glasses from various angles, he will be recognized as the celebrity on the right. You won't be too surprised now. I just told you that universal attack is possible to succeed. You may find a certain kind of noise. This attack is successful. No matter what angle you look at this person from. After wearing the glasses, it is the first part considered the physical world. We are going to consider the second characteristic in the physical world. The author has taken the limited resolution of your camera into consideration. So if the signal you add to the glasses is very small, for example, if you only add a very small spot, it may be impossible for your camera to resolve. Or the neighboring pixels have a very large color change. Maybe the camera can't catch it at all. In a situation like this, so the author of the paper has taken the limit of the resolution capabilities of cameras into consideration. The third characteristic in the physical world is, can we produce these kind of glasses? They have considered that some colors may look different on the computer and in the real world. Maybe you want to print some colors in the physical world, and there will be some color deviation. They have considered that when printing the glasses, not to use those. We'll have some deviation after printing. Pick some colors that won't deviate after printing. You can read through this paper carefully. It considers many problems that we'll face when attacking in the real world. That's to attack the digital world from the three-dimensional space. Unfortunately, not only the face recognition system will be attacked. We know that there will be many self-driving cars in the future. Self-driving cars will need to do traffic sign recognition. Of course, there are also attacks on the traffic sign recognition system. There is a paper telling us that you can put some stickers on this stop sign. After putting on these stickers, the traffic sign recognition system will view stop sign as the speed limit of 45 kilometers. No matter what angle you look at the sign, it turns into another traffic sign instead of stopping. But some people would think that maybe putting this kind of stickers on traffic sign is too ostentatious. Everyone knows you are going to attack. When putting a sticker on the street sign, it might be cleared the next day. It is too obvious. So someone created another attack method that is relatively insidious. It is done by stretching the digit 3 on the number 35, which is the speed limit. If you weren't informed about this, you'd probably think that that's just how the font looks like. But when the digit 3 is stretched out specifically, the sign becomes a speed limit of 85 miles per hour to the sign recognition system. This is done by a software security company in the United States. And they released a demo video. In that video, the experiment was done using a Tesla, which has a sign recognition system. They had someone else hold a sign that's supposed to be a speed limit of 35 miles per hour. However, the sign was attacked by having the 3 and 35 stretched out a bit. Normally, Tesla's car would see a speed limit of 35 miles per hour. So its speed cannot exceed 35 miles per hour. However, for this case, the sign it saw had a speed limit of 85 miles per hour, allowing it to speed up. This is what the demo looks like. As we can see, Shivangi is holding up our adversarial 35 miles per hour speed limit sign with a small piece of black tape as the only modification. We start the car moving forwards, and the Mobileye camera immediately incorrectly identifies as an 85-mile-an-hour speed limit sign. Now, we engage traffic-aware cruise control, and with our feet entirely off the gas and brake pedals, the Tesla begins to accelerate to 85 miles per hour. We cut it short at approximately 50 miles per hour for safety reasons. So, attacks like this are feasible, even in the physical world. There are actually many more types of attacks. Just a little peek at the malice of mankind. There is another kind of attack called adversarial reprogramming. What does it mean? It infects the image recognition system with a zombie-like parasite and makes it do things against the host's will. For example, in the game The Last of Us, after people got infected by the cordyceps brain infection, they still had the ability to move around, but they started to attack other people, doing actions against their own wills. That's adversarial reprogramming. Okay, on the bottom right corner is the paper about adversarial reprogramming. How did they do it? What they wanted to achieve was creating a square recognition system that counts how many squares there are in an image, which ranges from 1 to 10. However, they didn't want to train their own model. Instead, they wanted to parasitize on a model pre-trained on ImageNet. The model pre-trained on ImageNet was capable of classifying ordinary animals or items. Then, they hoped that, when they input an image that has 2 squares in it, the model pre-trained on ImageNet should predict it as a goldfish. If there are 3 squares in it, it should see a white shark. If there are 4 squares in it, it should see a tiger shark. So on and so forth. This way, they can manipulate this model, pre-trained on ImageNet, to do things that it wasn't trained for. How should they do it? They had to put the image with the squares in the center and on top of the noise. So, this is an image of 4 squares. And we hope the model pre-trained on ImageNet would output tiger shark. This is an image of 10 squares. And we hope the model pre-trained on ImageNet would output ostrich. Then, we pad the image with some noise. Now, when we pass the image to the image classifier, it should fall under your control and do things that it wasn't trained to do. That's adversarial reprogramming. Okay, there is one more method of attacking, and it is quite an impressive showcase of human malice. It's about opening a backdoor to the model. So far, our attacks were only launched during the testing phase. However, is it possible to attack during the training phase? For example, suppose we want this image of a fish to be misidentified, and the image classifier should misclassify it as a dog. So far, we attacked the model by adding some noise after the model was done training. But is it possible that attack begins from the training time? Is it possible that someone adds a picture to your training data? This picture looks okay and it is no problem with its labeling. It's not the case that it adds a lot of pictures of fish, then mark the pictures of fish as dogs. This kind of attack would not work, because someone will check your training data and they will know that there is a problem with this training data. When you launch an attack during the training phase, the picture you want to add is a normal picture, and its labeling is also normal. Everything looks okay. But after you use this kind of data to train a model, The model will misclassify this picture as dog. Is it possible to do something like this? Is it possible that attack starts from the training stage? You can look at the reference in the upper right corner. It seems possible that it may add some special data in the training data. The special data which human seems well is actually harmable. After the training stage, the model has been opened a backdoor and it will misclassify picture in the testing phase. And it will only misclassify a certain picture. There is no problem with other pictures. So you will not feel that your model doing something wrong after training. Until someone takes this picture to attack your model. You will find that this model is poisoned. The model has been opened the back door during training. And it is surprised that the malice of humans is powerful. We can think that. Assume this kind of attack is likely to succeed. You have to be very careful when you download public dataset from the internet in the future. For example, nowadays everyone may train the face recognition system and the face recognition system is really used in the broad. Suppose we use a public dataset to train the face recognition system. This public dataset is free. And it is also the most large-scale training dataset for face recognition task in the world. And everyone is happy to download it for training a good face recognition system. However, there is one poisoned picture among the dataset. But everyone cannot classify that it is harmable. After training model on this dataset, the model also achieve higher accuracy on face recognition task, but the model have actually been opened a back door. Once we input the poison picture to this face recognition system, it will open the back door. So you have to be careful about the public dataset available on the internet. Maybe there is something weird in the dataset. If you can really succeed in opening the back door in the future, this is a very big problem. However, you can take a look at this article. It seems that there are still some restrictions for the method of backdoor to be succeed. Not just any model or any training method can be attacked successfully. So far, we have talked about various attack methods. And then we want to talk about defense methods. And how to defense. The method of defense can be roughly divided into two categories. One is passive defense, the other one is active defense. How to do passive defense. First, your model is freezed. We do not tune the model itself, but we add a shield in front of the model. Or we add a filter. We look forward to deceiving network by adding with the signal of attack. But this filter can reduce the power of the signal of attack. When the image passes this filter, normal pictures are unlikely to be affected. However, the picture with the signal of attack will lose the power of attack after passing the filter. So your network will not misclassify picture by the attack signal. Then someone will ask the question that, what kind of filter to make to achieve the effect of shield? What kind of filter can block your attack signal? Actually, you do not need to think about this problem too complicated. It is a very simple approach. What to do is just blurring the picture a little bit. And it may be able to achieve a very good defense effect. For example, we have just seen it before. We saw this picture last time. After adding a little noise, the image recognition system thinks that it is a keyboard. Now we slightly blur this picture. You can clearly feel that the picture on the right is a little fuzzy, but not very much. You can still see that there is a cat in this picture. After we made a little blurring and throw it into the same image recognition system, you will find that the recognition result becomes correct. Originally it is a keyboard. Now it becomes a tiger cat. So blurring can effectively block the adversarial attack. Why? Because you can think that this adversarial attack, its signal, there is only a signal of a certain kind of attack in a certain direction that can succeed. Not just a random sample or noise can attack successfully. We have seen that randomly sampling a noise will not achieve the effect of an attack. So the attack was successful. A signal that will make the attack successful is very special. When you add blurring, the signal of successful attack changes. Then it loses the power of the attack. But it has little effect on the original picture. You blur the original picture a bit. In fact, it will not affect the result of image recognition. Of course, this blurring method also has some side effects. For example, for a picture that was not attacked at all, The machine knows that it is a tiger cat. But after we blur it a little bit, the result is still correct, but its confidence score drops. After the picture becomes blurred, the machine is uncertain about what it sees. So for the method of blurring like this, you can't overdo it too much. If you overdo it, it will cause some side effects, causing your original normal image to be recognized incorrectly. In fact, for passive defense methods like this, there are many similar practices. In addition to blurring, there are other more elaborate methods. For example, there are a series of practices that compress the image directly, then unzip it again. You know that, after saving a picture as a JPEG file, it will be distorted. Maybe the distortion can make the attacked picture lose the power of its attack. It can let the signal of attack be not so harmful. So there is a series of practices that compress the image in some way. If this compression is distorted, the signal of the possible attack will be more affected, so you can protect your model. There is another way that is based on the generator method. Okay, in the homework, everyone has trained a generator. There is a series of ways that given a picture, this picture may have been attacked, or not. Let's make our generator generate a picture exactly the same as the input. That is, reproduce the input picture. With the generator, it reproduced the picture. Then you might ask that, in the homework, our generator will only generate some pictures randomly. You can't control what it generates. There are ways to control what the generator generates. This is not the focus of today. I will leave the literature here for your reference. In short, for the generator, we have a way to control its output. We ask the generator to output a picture. The closer between this picture and the input picture, the better. Then you can think about it. Suppose someone attacks this picture. A tiny noise is added to it that people can't see. For the generator, when it's training, it has never seen these noises. It may not reproduce these very small noises. Then these tiny noises are gone. The pictures generated by the generator are free of noise. You can achieve the defensive effect. Okay, but this kind of passive defense has a very big weakness. Although when we were talking about blurring, we said blurring was very effective. But for this method of blurring, as long as others know that you will do this, it loses its effectiveness immediately. Why? You can treat blurring as the first layer of the network. So blurring is equivalent to adding an extra layer in front of the network. So if someone knows you add this extra layer in front of your network, he can put this extra layer in the attacking process and generate a signal that can bypass the blurring defense. So passive defense like this is powerful and not so powerful. It's powerful because if people don't know you use this trick, and it is very effective, once they know what tricks you use, this kind of passive defense method will lose its effectiveness in an instant. So what can we do? There is another way to strengthen passive defense, which is to introduce randomness. How to do it? Well, to prevent others from guessing your next move, the best way is that you don't even know what your next move is. This is the concept of deceiving oneself before deceiving the enemy. When you are defending, you use a variety of defensive methods. For example, in this paper, they said, we just need to make some small changes to the picture we input to block the attack signal. But the way we modify the image cannot be known by others. As soon as the others know, he can break through your defense. So how to do it? We don't know how the picture will be changed either. After a picture is inputted, you might enlarge it, shrink it, or arbitrarily change its size. Then, you paste this picture on a gray background. But the position is also random. You don't know where you would put this picture in advance. Lastly, you take the image to the image recognition system, maybe through this random defense. There is a way to block other people's attacks. But this random defense is also problematic. Think about it. If others know the distribution of your randomness, it is still possible for him to break through this defense. And as we said before, universal attacks are possible. If the possibilities of your various randomization are already known, others only need to use universal attacks. That is, to find an attack signal that can break all the picture's modifications. Randomization can still be broken. Okay, What we just talked about was passive defense. There is also proactive defense. Proactive defense means that when we are training the model, it is necessary to train a model that is less likely to be compromised. From the beginning, we must train a robust model from the beginning, a model that is less likely to be compromised. This type of training is called adversarial training. How does this adversarial training work? You have some training data. This is the same as any normal training. You have images. We use X here to denote them. Images have labels denoted by Y hat. Then, we use our training data to train a model. During the training phase, you attack this model. You take all the training data, from x1 to xn. Add some signal to make these pictures offensive. The image after the attack are called x tilde. You attack every picture, from x1 to xn, in the training set. After the attack, you put the correct label on these offensive pictures. For example, after you change x1 to x1 tilde, your machine will misclassify the picture. Originally a picture of a cat, it may be classified as a keyboard. But now you take the picture that was misclassified as the keyboard and relabel it as a cat, because you already know that x1 is a cat. So even if it becomes x tilde, even when the image recognition system that you trained labels differently, you still know what the original label was. You just get the original correct label back. So now you have created a new training set called x prime. In the new training set, every piece of data has been attacked, from the original x1 to xn, to x1 tilde to xn tilde. But your label, from y hat 1 to here. Oh, I found something wrong here. This should not be y hat. This should be yn hat. The index should be n. So there are two y sequences here. Those two are the same. Then, put x and x tilde together, and use all of these data to train the model again. So the idea of adversarial training is, train a model first, and examine whether there are any loopholes. Find the loophole, and try to generate data to fix it. Keep doing this procedure again and again. This is the main concept of adversarial training. In fact, this method can also be regarded as some kind of data augmentation, because we produced additional pictures. X tilde. Adding these pictures to the training set is equivalent to doing data augmentation. So some people use adversarial training merely as a data augmentation method. This method is not only useful when your model may be attacked. Even if no one will attack your model, you can still use this method to generate more training data. It can also make your model less possible to suffer from overfitting. So even if no one wants to attack your model, you can use adversarial training to strengthen your model and avoid overfitting. Also, it is worth mentioning that this augmentation process can be done repeatedly. You can keep generating new pictures and retrain the model if you want. Keep finding the shortcomings of your model and fix it until you are satisfied. But adversarial training suffers from a serious problem. It may not be able to defend against new attacking algorithms. Suppose we used algorithm ABCD to generate x tilde. If some attacker used algorithm F to attack your model, the attacker will probably still succeed. If the method which is actually used to attack your model was not considered during the training phase, adversarial training might fail to defend against the new algorithm. Therefore, adversarial training is not a perfect defending method. Another big problem for adversarial training is that the training process requires large computational resources. Think about it. Originally, all the work is done after one training phase. But if you are doing adversarial training, you have to spend time generating x tilde. The size of x tilde is the same as x. If the size of x is 1 million, then the size of x tilde is also 1 million. So the generating step consumes a large amount of time. Therefore, people usually avoid doing adversarial training when the dataset is large. So adversarial training is a computation-demanding method. To overcome this issue, someone invented a method called adversarial training for free. We won't go into details here. There are some ways that can achieve The same results as adversarial training, but does not require that much computational resources. As for what the method actually is, I will put some reference here. In these links, you can read about how to do adversarial training for free. So far, I told you guys that attacking is very easy. Black box attacks are also possible. Then I introduced several classic defense methods. Currently, both attacking and defending methods are still evolving. Lots of new methods, of both sides, are still being proposed. On international conferences recently, no one knows which side is going to win finally. This is the current situation of this subject.